infinity, by varying z value from minus infinity to plus infinity, you will have an infinite plane here. You can have an infinite plane, something like this. Let me redraw it here. Suppose you fix the value of your phi and you do not fix the value of your rho. Rho can go up to plus infinity from 0 to this, and your z value can go from minus infinity to plus infinity. So this will be the infinite plane. The infinite plane. So this, the equation of this surface is phi equal to C2. The equation of this surface is phi equal to C2. Phi equal to C2 is your coordinate surface. Then another coordinate surface we can think of is z equal to C3. So what is z equal to C3? You just imagine a coordinate system like this. So let's say z value is equal to C3 constant. So if you vary rho from 0 to infinity, it can extend up to infinity in all the directions. If you vary phi from 0 to 2 pi, and you will have some kind of infinite plane like this. Infinite plane that will have an equation of z equal to C3, infinite plane. So the coordinate surfaces are infinite plane perpendicular to z-axis, infinite plane through the z-axis. Here it touches the z-axis, infinite cylinder coaxial with the z-axis, extending from minus infinity to plus infinity. And yeah, I have also talked about this rho equal to C1. Yeah, intersection and all. You can just go back. I will just go back to that here. Where is that? I think I can explain it from this picture. Yeah. So intersection of the coordinate surface. The coordinate surface for z equal to C3 is a certain constant like this, and this is your phi equal to C2 surface, and your curved surface is rho equal to C1, rho equal to C1 surface. So if you consider the intersection of rho equal to C1 and z equal to C3, rho equal to C1, as I have just explained, it is a infinite cylinder extending from minus infinity to plus infinity, and you have rho z equal to C3, which is a infinite plane cutting the z-axis. Infinite plane cutting the z-axis at 90 degree. So you just consider an infinite cylinder piercing through such plane, infinite cylinder piercing through such z equal to C3 plane. So the intersection, as you see, it is a circle. The intersection of rho equal to C1 and z equal to C3 is a circle here. And if you consider the intersection of rho equal to C2 and z equal to C3, z equal to C3 is this plane, rho equal to C2 is this plane, which is passing through the z-axis. So you just consider these planes, phi equal to C2 and z equal to C3 plane. You will find that the intersection is this line. The intersection is a straight line. And if you consider rho equal to C1, which is a infinite cylinder, and phi equal to C2, which is this plane, the intersection of this infinite cylinder and this plane will be this, another straight line. The intersection of phi equal to C2 and rho equal to C1 is this plane. Okay, the intersection is this plane. So these are all written here. Intersection of rho equal to C2. You just picture it yourself. Try to picture it yourself. Think about it. Intersection of these two surfaces. Intersection of this surface is also a straight line. However, intersection of rho equal to C1 and z equal to C3 is a circle. So please go through it and picture all this plane as I have already explained. Now, yeah, what are the scale factors now? So the scale factors h1 will be written as h rho, h2 is corresponding to your phi2 coordinates written as phi h5, h3 will be written as z. Here u1 is rho, u2 is phi, u3 is z. Okay, so your position vector in Cartesian is this. Position vector in cylindrical system. Position vector in cylindrical system will be like this. X is rho cos phi in the transformation. In the transformation relation, X is rho cos phi, Y is rho sin phi, Z is Z. So following that, this is the position vector in cylindrical coordinate system. Now you can calculate your scale factor, or you can calculate the tangential unit vector also. What is the scale factor now? Is rho will be del r upon del rho. See, it was h1. It was h1 is equal to del r upon del u1. So in this cylindrical coordinate system, u1 you replace with rho, h1 you replace with h rho. Okay, so if you do that, del r upon del rho, so differentiate this with rho, then you will get cos theta I plus rho sin theta, cos phi I plus sin phi j, plus differentiation of z with respect to rho will be 0. And then this is what you will have after differentiation. You just take the magnitude. This is square root of cos square phi plus sin square phi, that will be 1. So h rho, the scale factor corresponding to rho coordinate line is 1. The scale factor corresponding to phi coordinate line you can similarly obtain by differentiating your position vector with respect to phi. Instead of differentiating for obtaining h2, you usually use del r upon del u2. So, but in place of u2, you now have your phi. In place of h2, you now have your h phi. Okay, simple as that. So differentiate cos phi, you will get minus of sin phi. Differentiate sin phi, you will get plus of cos phi. Then if you take the magnitude of that, then this will be rho square root of cos square plus sin square. That will be rho. Okay, sin square plus cos square is 1. And differentiate with respect to z, then you will have the scale factor corresponding to h3 or hz. Then differentiation of this quantity with respect to z is 0. This quantity with respect to z is 0. The differentiation of z with respect to z is 1. So your hz is also 1. So you can obtain the scale factors like this. Then after that, we can obtain the unit vectors also. So the scale factors are known to us already. H rho is 1, H phi is rho, H z is 1. So this is your position vectors. How do you obtain your unit vectors? In order to obtain your unit vector, the first unit vector E1, instead of E1, I'm now going to use E rho. E rho will be del r vector upon del rho upon del r vector upon del rho. Right, so del r upon del rho is, if you differentiate this, this is what you will get, cos phi I plus sin phi j, and differentiation of z with respect to rho is 0. And this scale factor, this is a scale factor that is 1. So this is the unit vector is simply cos phi I plus sin phi j, like that. Similarly, you can obtain your E2, which will be your E phi, and del r upon del phi upon your h phi. And you can also obtain your E3, which will be Ez del r upon del rho upon, del r upon del z. This is phi. Okay, this is phi, h phi. This is phi, this is h phi. Here in this case, del z is z. So like that, you can obtain the unit vectors E rho and E phi and Ez. All these quantities you can obtain. Then once you have the unit vectors, you can show that this cylindrical coordinate system is a curvilinear coordinate system. How do we prove that this is a orthogonal? You can prove that this is a orthogonal system. Orthogonal system. How do we know that our cylindrical system is orthogonal? You can verify it by taking a dot product, E rho dot E phi. what will be E rho dot E phi? This will be cos phi I sine phi j dot product with minus of sine phi I plus cos phi j. This will be cos in this will be I dot I is 1 minus of sine phi cos phi plus j dot j is 1 sine phi cos phi. This will be 0. That means the dot product between two unit vector is 0. Now, if you take the dot product between E rho and Ez, E rho is what? Cos phi I plus sine phi j cap dot your Ez is k cap. So I dot k is 0, j dot k is 0. This is also 0. And similarly, you can see that E phi dot Ez cap, this would be minus of sine phi I plus cos phi j dot product with k. This is I dot k is 0, j dot k is 0. So this is also 0. So that means when you take a dot product between all these three tangential unit vectors in a cylindrical coordinate system, they are mutually perpendicular, because the dot product, as you know it, it's a magnitude of the first vector, magnitude of the second vector, and cosine of the angle between them. If this quantity is 0, that means your theta is 90 degree. The angle between the two vectors is 90 degree. Only then the dot product can be 0. So this way, by taking the dot product among these unit vectors, you can show that this cylindrical coordinate system, it is a curvilinear system, but it is also orthogonal system. So therefore, cylindrical system is a orthogonal curvilinear coordinate system. Now, these are certain identities in curvilinear system that you can easily solve. This is just to show that del, or there are differentiation of E rho with respect to time is this phi dot e phi cap. So differentiation with respect to time, you just put e rho, the unit vector, tangential unit vector along the rho coordinate is this. So differentiation of this, so you assume that this, other than your I and j cap, I and j cap, you know that they are unit vectors, so they are vectors having unit magnitude. So there is no point in differentiating this. There's no point in differentiating this. Okay, so this is always 0. There's no point in differentiating this with respect to time or any other variable at all, because they are unit vectors. Unit vectors means constant. They have a unit magnitude, that means they are constant. So you cannot difference, whenever you differentiate with any variable, this is 0. So no need to differentiate your I and j here with respect to time. So the only thing you can differentiate is your cos phi and sine phi. So when you differentiate cos phi, you will get minus of sine phi. Then the differentiation of this phi variable itself, d phi upon dt. You can differentiate sine phi. Differentiation of sine phi is plus of cos phi. Then differentiation of this variable with t. Okay. So d phi upon dt, you can take it as a common factor, and this is minus of sine phi I cap plus cos phi j cap, and this is your phi dot. This is your phi dot, and this is your e phi. So this is your e phi. Your e phi unit vector along tangential unit vector along the phi coordinate is this. So there you can write it as this. Okay. So this is simple solution. I think you can also follow the similar calculation, knowing for the fact that I cap and j cap are constant unit vectors. So the only thing you should differentiate here again is your phi, your sine function of phi and cosine function of phi. Okay, so please follow the steps like I explained before. And yeah, this is what I have already discussed. Yeah. Now, this is another simple thing that you have to come across in cylindrical coordinate system. So as I said before, your engineering or physics problem might be simplified if you consider this cylindrical coordinate system rho, phi, and rho, phi, and z coordinate system. So here we know that the scale factors are 1, rho, and 1, right? So the gradient of this gradient of phi, as we know it, this is what was that? E1 cap upon H1 del upon del U1 phi plus E2 cap upon H2 del psi upon del U2 plus E3 cap upon H3 del psi upon del U3 del psi upon del U3. So just substitute E1 as E rho cap, E2 as E phi cap, E3 cap as your EZ cap. And in place of U1, you simply put rho, U2 you put phi, U3 you put Z. In place of H1, you put H rho, which is 1. In place of H2, you put H phi, which is rho. In place of H3, you put Hz, that is 1. So simply put all these scale factors and the coordinate variables, and this is your gradient of phi in gradient of psi in cylindrical coordinate system. Gradient of psi in cylindrical coordinate system. Okay, and this was the general expression for orthogonal curvilinear coordinate system. You just put the value of the scale factors. H1 is 1, H2 is rho, H3 is 1. Then the final quantity here is rho. So U1 in place of that, U1 coordinate variable, you now have phi coordinate variable. In place of U2, you have rho, sorry, here in place of U1, you have a rho coordinate variable. In place of U2, you have a phi coordinate variable. And similarly for here z coordinate variable, then you put the value of the scale factors h1 h2. So this is your divergence. And similarly, I think you can write the cal here. Cal, as we know it, it was h1 h2 h3, right? And this was h1 e1 cap, h2 e2 cap, h3 e3 cap, del upon del u1, del upon del u2, del upon del u3, and a1, h1, a2, h2, a3, h3. So simply put the values of the scale factors and the coordinate variables, replace them. u1 with rho, u2 with phi, u3 with z. Then you will obtain the cal. So all this vector operation, you can do it in this cylindrical coordinate system. So you can solve your engineering or physical problem using this cylindrical coordinate system. And here is also another thing. If you have a vector, if you are going to work in a cylindrical coordinate system, if you are going to solve your vector problem in a cylindrical coordinate system, you should be able to write your vector in a cylindrical coordinate system. So first you have to see what are the transformation relations. X is rho cos phi, y is rho sine phi, z is z. Then in place of your I cap, you know that you have a unit vector rho e rho, e phi, and ez. So you have to write an express here. You are having e rho in terms of I and j, e phi in terms of I and j. Now, in order to express this in a cylindrical coordinate system, you should be able to write your I cap in terms of e rho and e phi. So what we are going to do is that we are going to multiply this e rho with cos phi, multiply with cos phi. Then once you multiply with cos phi here, e rho cos phi, this will be cos square phi I cap, and this will be sine phi cos phi j cap. Now if you multiply this with minus of sine phi, then you will get minus of e phi sine phi, and then this will be plus of sine square phi I cap plus sorry, multiplying with minus of sine phi, minus of sine phi cos phi j cap. So my handwriting is very poor over here. Now if you add these two here, this will be e rho cos phi minus e phi sine phi, and this will be sine square phi plus cos square phi into I cap, and this will cancel out. So therefore you can write your I cap as e rho, you can write your I cap as cos phi e rho minus of sine phi e phi. Like that you can write your, express your I cap, you can express your j cap, and you can express your k cap. K cap will be simply z. So you put all these things. So here like you can express your j cap, you can express your I cap, and then you just substitute here in this cylindrical coordinate system. So this is your vector A in terms of cylindrical coordinate system. Vector A in terms of cylindrical coordinate system. So this is what we know it as your A1. This is your, what we know it as your A2. This is what you know it as your A3. As you see, A1 is Z cos phi minus 2 rho sine phi cos phi. Or A1 you can write as, A1 is actually a function of rho, phi, and Z. So this is what I meant by saying that at the beginning here in the cylindrical system discussion also, A1 is a vector field. The vector field A can be a function of the coordinate variables like u1, u2, and u3. So here the coordinate variables are rho, phi, and z. So these coefficients are a function of the coordinate variables u1, u2, and 3. Okay. So this is the last section. I don't know if it is too much for you. I think I can stop. Okay. So I can stop now, and tomorrow maybe if I have a free time, I will I will inform you the time. Then we can finish this spherical coordinate system. We can discuss about the spherical coordinate system. It is more or less same as your cylindrical coordinate system. And after that, we can continue with our what is that, tensor analysis. Tensor is another section that I need to cover under this unit. So if you have typed your attendance, you can exit the meeting. Tomorrow I can share this video, probably, most likely. Okay, you can exit the meeting. Thank you, everyone.